Hey, this is Ronald, and we're going to talk about my lab report on Faraday's law. This experiment explores how a changing magnetic field induces an electromotive force, which is EMF. EMF can drive an electric current, and we investigate this by observing a magnet falling through a conductive tube and analyze the dynamics of this interaction. In this experiment, a bar magnet is dropped through a vertical aluminum tube. The key observation is that the magnet's fall is significantly slowed compared to the free fall. This slowing effect demonstrates the influence of electromagnetic induction. As a magnet falls, its changing magnetic field induces currents within the tube. This induced currents generate their own magnetic field that opposes the motion of the falling magnet. The time it takes for the magnet to fall through the tube is measured. It took around like 5.3 seconds. This time is then compared to the expected fall time under gravity alone, highlighting the retarding effect of the induced currents. To understand this phenomenon, a computational model is coded, like is developed. The model simulates the aluminum tube as a stack of conductive rings. The core of the model involves these calculations. Um, Magnetic field calculation. Magnetic field of the falling magnet is treated as a magnetic dipole and is calculated at various points along the tube. Flux change. The rate of change of magnetic flux through each ring is determined as the magnet passes. Induced current. Faraday's law is applied to calculate the current induced in each ring based on the changing flux. Lorentz force. The magnetic force exerted on these induced currents by the magnet's field is calculated using the Lorentz force law. Newton's law. Newton's laws of motion are used to determine the net force on the magnet and update its velocity and position as it falls through the tube. The simulation allows us to visualize and quantify the force at play, providing a theoretical prediction of the magnet's motion. Comparing the model's prediction with the experimental results is crucial. Ideally, the simulated fall time should be close to the experimental fall time. The differences uh, can arise, the errors can arise from simplifying assumptions in the model. The primary assumptions include the magnet is modeled as a perfect dipole, the tube is represented by a series of independent rings, the resistance of the tube is assumed to be uniform, edge effects and imperfections in the tube's geometry are neglected. The model provides a good experiment approximation, but these assumptions can lead to deviations from the experimental results. What if? Let's consider two hypothetical scenarios. Zero resistivity. The tube's if the tube's resistivity were reduced to near zero, approaching superconductivity, the induced currents would become extremely large. This would result in a much stronger opposing magnetic force, causing the magnet to fall very, very slowly. The magnetic field breaking effect would be maximized. If holes or slots were cut into the tube, the continuous circular path for the induced current would be disrupted. and this would reduce the magnitude of the induced currents. As a result, the opposing magnetic force on the magnet would be greatly diminished, and the magnet would fall much faster, nearly like a free fall. In summary, this experiment demonstrates Faraday's law of induction. The falling magnet induces currents in the aluminum tube, and these currents create a magnetic field that opposes the magnet's motion. The computational model provides a valuable tool for understanding and predicting this behavior. And what if scenarios highlight the crucial role of the tube's conductivity and its geometry in determining the strength of the induced currents and the resulting magnetic forces? Thank you.